Welcome to the next session of Finite Automata. In the previous sessions, we discussed regular expressions, DFA, NFA, etc. In the current session, we are going to discuss mainly about regular grammars. Regular grammars. Let us go through the video how grammars are derived. What is the relationship between regular language and regular grammar? How we can define a regular grammar? For that, let us move through the slides. In the current session, we introduce regular grammars. Regular grammars denote syntactical rules for conversion in natural languages. The natural languages such as English, Sanskrit, etc. They have attempted to define grammars. Linguistics have attempted to define grammars. The theory of formal languages finds its acceptability and applications extensively in the field of computer science. In the field of computer science, in 1956, a person named Noam Chomsky, he developed a mathematical model of regular grammar. A mathematical model was developed by Chomsky in 1956. It is effective for writing computer languages. It is effective. The mathematical model developed by Chomsky in 1956 is an effective model for developing regular grammars as well as, in essence, computer languages. We shall define a regular grammar. What is meant by a regular grammar? How it can be defined? It is normally defined as a four-tuple element. Four tuples. N, T, S, and P. N denotes a set of non-terminals. T denotes a set of terminals. S is the start symbol and P is a set of production rules. A set of terminals denoted by N. Some others represented it as Vn, a set of variables. And second, a set of terminal symbols denoted by T. In some text, it is represented by sigma. And S is a special variable. It is the starting state. It is the start symbol. It is an element of non-terminal symbols. S element of N. P is production rules for terminals and non-terminals. A set of productions. How these non-terminals can be derived to the terminal symbols. That is the set of production rules. A production rule has the form alpha derives beta. Alpha can be derived into beta. The left hand side, it is denoted by alpha. Alpha and beta are strings on non-terminals union terminals, and at least one symbol of alpha belongs to the set of non-terminals. A production rule has the form alpha derives beta, where alpha and beta are the strings on a set of variables or non-terminal symbols, union the set of terminal symbols. And at least one symbol of alpha belongs to the set of variables or non-terminal symbols. For example, consider the grammar G1. Consider the grammar G1. N is equal to set S A B is the first tuple. Second tuple T is equal to set A comma B. third start symbol it is S, and the fourth production rules. S derives AB. Capital A derives small a. Capital B derives small b. This is an example of grammar. S, A, B are non-terminal symbols. A and B are terminal symbols. S is the start symbol and the productions P. S derives AB, A derives small a, and B derives small b. This is an example of grammar G1. Consider one more example, grammar G2. Here we can say that a set of non-terminals, set SA, set of terminals AB, and S is the start symbol, and production rules. S derives small a, capital A, small b. Small a, capital A derives small a, capital A, and A derives an empty string epsilon. S and A are non-terminals. Small a and small b are terminals, set of terminals. S is the start symbol. Epsilon is the empty string. And the production rules P denoted by S derives AAB, AA derives AAAB, and A derives epsilon. It's another example of grammar. In this grammar, we have a set of symbols as well as an empty string also. So, empty string also can be denoted in regular grammar. Derivations from a grammar. Strings may be derived from other strings using the productions in a grammar. If a grammar G has a production alpha derives beta, we can say that alpha derives beta means x alpha y derives x beta y. This derivation can be written as x alpha y derives x beta y based on the regular grammar G. Based on the regular grammar G. A set of strings can be derived from other strings using these production rules. That set of strings derived is known as derivations from a regular grammar. For example, let us consider an example. The same grammar we already shown in example. N is equal to SA, T is equal to AB, S, T is equal to S derives AAB, AA derives AAAB, A derives epsilon. The sum of the strings that we can derive. S derives AAB. Small a is a terminal, capital A can be considered as epsilon and small b. It means that we got the string AB. It is one derivation. Consider one more derivation. S derives AAB. AA can be derived as, this can be derived as AAAB, and there is a last B. Then AA, capital A can be derived to epsilon and BB. Means that AABB is a string that can be derived from S. Consider one more example. S AAB AA can be derived as AAAB, and there is a last B. AA can, first is this, and this AA can be derived as AAAB, AAAB, and there is another 2B. and A is terminal, A is terminal, A is terminal, capital A can be epsilon, B is terminal, B is terminal, and B is terminal. So A, B, B, B. Here itself we got three strings that can be derived from S. The first is AB, the second is AABB, the third is AAA, BBB, etc. A set of strings can be derived through this production. Language generated by a grammar. The set of all strings that can be derived from a grammar. We saw now in the previous example, we got a set of strings AB, AABB, AABBB, etc. Several strings can be derived. This set of all strings derived from a regular grammar is said to be a language generated from that grammar. A language generated by a grammar, G is a subset formally defined. L of G is equal to set W such that W element of sigma star S derives W based on regular grammar. If the regular language of a regular grammar is equal to a regular language of another grammar, that is, if L of G1 is equal to L of G2, what does it mean? It means that both G1 and G2 are identical. The grammar G1 is equivalent to grammar G2. For example, consider a grammar. Consider a grammar. N is equal to set SA, set SA. Terminals set A comma. S is the start symbol and P production rules. S derives AB. A derives small and B derives small. We shall derive a string. S derives AB. It means that capital A can be derived to small a and capital B can be derived to small b. So the language derived from the particular grammar is set AB. Here S produces AB and can be replaced by small a, small b. The only accepted string is AB. That is, language of regular grammar G is equal to set AB. Consider one more example. In this case, the language generated can be AB, A square B, A B square, A square B square, etc. up to n times. Since A and B are different, we can generalize it into set A raised to M, B raised to N such that M greater than or equal to 0 and N greater than or equal to 0. Then moving to the next topic, construction of a grammar, generating a language. Construction of a grammar. How a regular grammar can be constructed. Given a language L of G, its corresponding grammar G represents the production rules which produces the regular language. Consider the language L of G. L of G is equal to set A raised to N, B raised to N, N greater than or equal to 0. The regular language is the set of strings, set epsilon AB, AABB, AAABBB, since n equal to, if n equal to 0, we get epsilon. If n equal to 1, this set AB. If n equal to 2, A square B square, that is AABB. If n is equal to 3, A cube B cube, AAABBB, etc. We get a set of strings. For epsilon, we can say that the production rule can be S derives epsilon. S derives epsilon. For AB, AABB, AAABBB, we can say that all these start with A and end with B. In between there is S. So we can say that S derives ASB. S derives ASB. Combining these two, we can say S derives ASB or epsilon. S derives ASB or epsilon. The production rule can be formed as S derives ASB or epsilon. Therefore, the regular grammar G corresponding to the given regular language, the regular grammar corresponding to the regular language, it is S derives ASB or epsilon. S derives ASB or epsilon. Key points. Three different points we have to remain. For a given language L of T, there can be more than one grammar which can produce. The grammar is not unique. Multiple grammars or more than one grammar can be produced for a regular language L of T. The grammar corresponding to the language must generate all possible strings. It also means that the grammar corresponding to the language must not generate any string which is not part of that language. It generates all possible strings and it must not generate any string, even a single string that is not part of that particular regular language. These are the main three key points to be reminded by constructing a regular grammar from regular language. Then here is a problem to be solved, a multiple choice question. Which one of the following grammar generates the language L? Set A raised to I, B raised to J, I not equal to J. Here I have given four various options A, B, C and D. You work out the following grammar and check whether which grammar generates the regular language L is equal to A raised to I, B raised to J such that I not equal to. I shall discuss the answer in the next session. Right now, in this session, you go through the question. There is one more question. Language is equal to, regular language of G is equal to A raised to M, B raised to N. M greater than or equal to 0. M can be 0 and N greater than 0. N should be greater than 0. 1, 2, 3, etc. up to N. Find out the grammar which produces the regular language L of G. This is the second question. Work out this two. And the third question, language L of G is equal to A raised to M, B raised to N. M greater than 0 and N greater than or equal to 0. Similar to the previous, the condition is swapped or exchanged. In the previous one, M greater than or equal to 0 and N greater than 0. Here, M is greater than 0 and N greater than or equal to 0. Find out the grammar. Three problems are given to work out. In the current session, we mainly discussed about regular grammars. What is meant by a regular grammar? How it can be defined? How a regular language can be represented through a grammar? And how grammars can be constructed from a language? Both parts we have already discussed. I think you all understood what I have explained here. You go through the final three problems, try to answer it. If you have any clarification, you need any clarification, or you have any doubts, let me know. We shall discuss it in the next session. Okay, thank you.